So we know that in any magnetic material, B is the magnetic flux density. This is the flux density, and H is the magnetic field intensity. Intensity of the magnetic field. Okay, field intensity. Okay. So we know that B and mu, the H are related as B is equal to mu naught mu r into H. Okay, where mu r is the permeability of the material. Okay. So B and H are linear if the mu is constant. B and H are linear, the magnetic curve will be linear when mu is a constant. Okay, but that is not the case in most of the magnetic material. For example, ferrite core, which we consider in the transformer, mu is not constant there. Okay, and as we increase the field intensity, the magnetic flux lines won't increase linearly in a ferrite material. So it depends on from material to material. That is why we need BH curve or BH loop. We call it as BH loop or hysteresis loop. Hysteresis loop. Okay, hysteresis loop. So as you can see here, we have this H, okay, magnetic field intensity. We are increasing the field intensity by increasing the current. Okay, by increasing the current, we are increasing the field intensity. So we are checking what is the density of the magnetic flux lines. How much magnetic flux lines are increasing in a particular area? Okay, in a particular area. Now that phi is equal to B into A. That means what are the flux lines which are increasing when we are increasing the field intensity of a particular magnetic material. So as you can see here, for a certain range, this magnetic intensity of the flux intensity will increase linearly. Linear increase will happen in the beginning. Then afterward, it's a non-linear zone. Then at one point, it saturates. Okay, that means even if you increase the field intensity after this point, even if you increase the field intensity or current after this point, there won't be any increase in the flux lines. There won't be any increase in the flux lines. That means the material has reached its saturation. Okay, so the flux density will remain constant even after this saturation. Okay, so uh, this is no more flux lines. That is why we call it as saturation. So there will be a curve. Okay, so this is the BH curve. There will be a loop. Okay, let us go and let us see what is BH loop. Okay, as you can see here, this is a loop. Okay, for example, we are increasing the flux lines H or I. So for in the beginning, it will increase like this. It is increasing like this. It is increasing like this. As you can see, this G and P. It is increasing to the G and P. At this point, it will be saturated. It will be saturated. That means there will be no more flux lines even if you increase H or I. Okay. So after this, let us say we are reducing or removing you are removing this field intensity or removing the current. Okay, if you remove the current, there will be some retentive magnetic field. Okay, there will be some magnetic field. It won't come to zero directly. As you can see here, this magnetic field will be retained. Okay, this magnetic field will be retained here. Okay, as it comes, the magnetic flux lines will reduce, but there will be a retentive magnetic field. Okay, so in order to remove this, in order to reduce this to zero, in order to bring the flux lines to zero, you have to apply a negative. So this is positive in a BH loop. You will have this. This is B positive. This is B positive. This is H positive, and this is B negative, and this is H negative. Okay. In order to reduce the flux lines, you have to apply a negative force. Okay, that is a coercive force you have to apply. So this will reduce at this point. At this point, it will reduce. So we generally call it as coercive point or C. Generally call it as coercive point or C. This point is generally referred as R, retentive point. Okay, the point of retentivity where the magnetic field will be magnetized. Magnetized material will be retained at this point. Therefore, we call it as retentivity. Okay, so in order to remove this magnetic field, you have to apply a negative H, and again it will come to a the magnetic flux lines will come to a zero. Okay, so if you keep on increasing, if you keep on increasing the field intensity in the negative direction, it will reach saturation. The magnetic field lines will reach saturation in the magnetic field lines will reach saturation in the negative side, negative saturation. This is negative saturation. it will reach a negative saturation. Okay. Again, in order to remove this, in order to if you keep on reducing the field intensity or reducing the current, it will come to this point where it is retained. It retains the magnetism. It retains the magnetism. Therefore, we call it as the point of retentivity. It will come to this point. Then again, if you increase the flux intensity in the positive direction, or if you increase the current in the positive direction, it will come to the magnetic flux density will come to a zero position. You are applying a coercive force. You are applying a coercive force in order to reduce the magnetic field. So this is called as coercive point. Then let us say again you are increasing. It will reach the point of saturation. This point of saturation won't change. Again, it will reach the point of saturation if you increase the magnetic field or current. Okay. So this loop is generally referred as hysteresis loop. This loop is generally referred as hysteresis loop. So if for a material like transformer, we need this hysteresis loop to be thinner, okay, because it's magnetizing and demagnetizing very quick. Okay, we are magnetizing and demagnetizing ferrite material of the magnetizing and demagnetizing ferrite material of the transformer very quick. Okay, so we need this hysteresis loop to be thin. We need this hysteresis loop to be thin because this is the loss in the core. This loss will occur in the core. Therefore, we call it as core loss, or hysteresis loss is a type of core loss which will occur due to AC excitation. So you need more power in order to remove the magnetism of the material. You need to apply much more power. Even by removing the AC excitation, you cannot completely remove the magnetization of the material. So you need much more power to remove it. So this loop, the area of the loop increases, the hysteresis loss increases. As this area of the loop increases, this hysteresis loss increases. So what can we do to reduce the hysteresis loss? What can we do to reduce the hysteresis loss in a magnetic material in a core? We can use thin loop materials like silicon steel in the silicon steel magnetic material whose hysteresis loop area is very thin. Okay, but for some applications you will be needing let's say you are electromagnetizing. Okay, you are using electricity to magnetize. For example, there is a rotor of a motor you need to magnetize. Okay, so for that it needs to retain its magnetism even if you are supplying less power. Okay, for that for any type of electromagnets, not only rotor, for any type of electromagnets, you can use a material which has higher hysteresis loop, which has thicker hysteresis loop. Okay, so this hysteresis loss is represented by this. This is the loss. The area enclosed by the loop is the loss in the core material of the transformer. So that's why we call it as core loss. Core loss also consists of eddy current loss. Core loss also consists of eddy current loss. What are eddy current loss? So when there is we know that the applied voltage, the voltage induced in the magnetic field is equal to n d phi by dt. Faraday's laws of induction says that the voltage induced in the induced EMF E is equal to n d phi by dt. Okay, but this induced EMF, whatever the induced EMF, it will be opposite to the source which is causing it. Okay, for example, let us say you are applying a voltage V. This applied voltage will induce a flux. In the magnetic material. This flux, rate of change of flux, will induce an EMF E. Will induce an EMF V. This induced EMF will oppose the source caused it. That means it will be negative of V. Okay, it will be negative of V. Therefore, it will allow a flow of current to flow through the ferromagnetic material. It will allow the flow of current to flow through the ferromagnetic material. This current, I square R loss or eddy current loss, this current which is opposite to the direction of the applied voltage will cause resistive loss or heat resistive losses. So that is what is known as eddy current losses. So how can we reduce the eddy current losses? So we are reducing the hysteresis loss by considering a thinner hysteresis loop material. Okay, like for example silicon steel. How can we reduce the eddy current losses? So if we can reduce the eddy current losses by considering less electric material. Okay, for example, even silica, when we consider silica steel is highly magnetic, but it is not electrical. Okay, so it will not allow the current to flow through its core. Okay, by considering materials like that, we can also reduce the eddy current losses. And moreover, we can consider the, instead of one single core, we can consider sheets of ferromagnetic material in between lamination. The lamination will stop the current from flowing, as it's a non-conducting material, a not electrically non-conducting material. So it will not allow the currents through flow through it. Therefore, by considering the insulated plates called laminations stacked together, the laminations stacked together in order to form the core, we can reduce the eddy current loss, which is caused due to the EMF, circulating EMF, which is caused due to the current because of the EMF, which is induced in the magnetic material. Okay, so the eddy current loss can be the formula for the eddy current loss can be written like this: P eddy is equal to pi square f square B max tau square divided by 6 rho. Okay, this can be, so rho is the resistivity of the material and tau is the thickness of the material. You know that B is the flux density, F is the frequency, and we are making it as a constant K. This we are making it as a constant K. So combination of eddy current losses and hysteresis losses, we call core loss in a transformer, which consists of eddy current loss and hysteresis loss. So I have described how to reduce the eddy current loss and hysteresis loss. And again, if you want me to repeat it, eddy current loss is reduced by considering by using laminations and by considering materials like which are non-conducting, electrically non-conducting in nature. Hysteresis loss is reduced by by considering a material which has thin area of hysteresis loop, thin hysteresis loop. That means it can be magnetized and demagnetized without losing much power. We can reduce the hysteresis loss in a transformer. Okay, so this is for the hysteresis loop, and because of which BH curve, the BH curve is the relation between the flux density and magnetic field intensity. For a linear, if we consider it is linear, so without saturation, if you consider it is linear, it will be like this. But most of the times, this, you know, that B is equal to mu into H. This permeability of the material is not linear. There will be a saturation. Therefore, the BH loop will be like this. So there will be a saturation after one time. Even if you increase the magnetic field intensity, flux density in the material will not increase. Therefore, we call it as a saturation. And I have also described the hysteresis loop, which is caused due to the retentivity of the magnetism in the magnetic material. In the next classes, we will study about the AC excitation of the magnetic circuit and so on.